So a simple and technical description would be saying that it is a data structure that holds historical transactional records, and it ensures security and transparency. But we can see it as a database that holds transactional data, as simple as that. And with transactional data, I mean not only currency like data like sending money or sending Bitcoin, it could be information. So its main purpose is to have a track of this history across the time. Next slide, please. So as you know, blockchain is composed by blocks. It's what its name says, but what is a block? So a block is the fundamental part of the blockchain. Its main purpose is to hold information. So it holds information about the transactions that has been made across the time in the of existence of the blockchain, but also holds information about the block itself, such as the timestamps, which is when this block was created. We will cover more about the block creation later, but yeah, also the blocks are identified by a hash, which is unique, and also by a height. And the height is basically how deep the block is in the blockchain. The deeper the block in the blockchain, the more recent this data is. So in this blockchain, each one of the blocks is related by each other by this hash. So can we go to the next slide, please? So as I mentioned, each one of the blocks is linked to each other by the hash. This hash is calculated accordingly to the information that the block contains. So this can be the transactional data, the time it was created. So this is to create a unique string, a unique key to identify a block. So this doesn't repeat. So if the information is changes inside the block, so will the hash of the block. So since I mentioned that each one of the blocks is related to each other by the hash of the previous block, well, here we have an example. So here we have 3 blocks, 1, 2, and 3. And the block 3 is related to the number 2 by its hash, and the number 2 is related to the number 1 by its hash. And the number 1, as you can see, since it doesn't have a previous block, it is called the Genesis block, which is the first block in the blockchain. This have a dummy previous hash, so because it doesn't point to anything. So according to in order to maintain consistency, for example, if we change the value of the transactions or anything, any data inside the block of in the block number 2, the hash will change, right? So instead of being 6BQ1, it will be a completely another thing. So the block number 3 will not know who to refer to, because the hash 6BQ1 doesn't exist anymore. So the blockchain will lose consistency. It will lose sense. Also, another thing that is important about blockchain is that it is a decentralized ledger. What does that mean? We will cover more about that later. But what it means is that no one holds authority over the network. And by that, it means that there is not a single person that decides what goes in and how it goes in inside the blockchain. So can we go to the next slide, please? So yeah, to make this simpler, we made an analogy. So basically, this is a book. So we want to add a new page inside the book. So we have a couple of editors that basically make the consensus to decide whether this page is added or not inside the book. So they together make a decision. For example, in this example, they say, yeah, this page that can be added to this book. So once they make a consensus, it is added to the book. So if the editors decide that, or at least the majority decide that it doesn't have to be inside the book, well, it is not added. So in this same way works the blockchain. So in this case, the book would be the blockchain, the page would be the blocks, the the editors would be the nodes. We will talk more this in the next slide, please. So the nodes are basically the participants inside the blockchain. So these are the ones that, as I mentioned, they make a consensus of whether the new information should be added or not inside the blockchain. These are the ones that receive the messages. So the messages could be new transactions, and they emit this new information through the whole blockchain. And once this message is emitted, I mean, this new transaction, they decide whether this information is consistent or not, and if it should be added or not inside the blockchain. So each one of the nodes are connected through each other using a peer-to-peer protocol. So there's no central hub. There's not a single node that can take arbitrarily the whole decisions of inside the blockchain. So each one of these holds a copy of the whole blockchain. This helps them decide whether the new information makes sense or not for the rest of the blockchain. So can we go to the next slide? So in a summary, we can say that blockchain is a decentralized database. Basically, no one holds authority over the whole network. It is a peer-to-peer network, as we just mentioned. Each one of the nodes are connected. Each one can emit and can receive messages. They can vote whether a new transaction should be added or not inside the blockchain. And also, it is immutable. This has to do that it is hard to change the information of the blocks. It would lose sense if we try to do that. So the information inside the blockchain cannot be changed. Next slide, please. So I'll leave you with David, which will help us through showing us an example of how blockchain works through code.
Okay, so this is David once again. Let me share my screen, just we can start coding a little bit. Wait a second. Okay, so let's get started. I want to introduce you how we are going to start developing this practical course. We will split this practical exercise into 3 parts.
Sorry, David. Sorry, can you make your font larger, please?
Yeah, sorry.
Thank you.
Thanks for the reminder. Is that okay?
That's perfect. Thank you.
Okay, cool. So as I was mentioning, we will split this course into 3 parts as the theory goes forward. Let's start first with the previous concept that we have seen before. That is, for example, how a block is created, what are the main properties of a block that a block has, and another file that we will be creating for setting up pretty much all the configuration for our blockchain application. Let me just, this is a very small application built in JavaScript, so we are not using any hard thing to understand, just plain JavaScript, and we are using Node.js to just install some dependencies for our application to run, right? So having said that, let's begin with the course. If you see, we have 2 files so far. This file will describe pretty much how a block will look like for our application. And as Esteban was mentioning, we will be starting describing the main properties for a block. So you see we have a timestamp. This is just to a unique identifier for this block, right? And we will have a second property for holding the transaction. Remember that a block can have transaction. And for example, in talking about blockchain specifically, blocks not only can have transaction, but for example, it can have any type of data that you want to process within the blockchain. There are some examples that, for example, manage official documents for make sure that they are authentic. And there are lots of examples that are not related just to cryptocurrencies, right? So for this example, we are just using some coins to store in here, some transactions, transferring some coins. And we will have another property that is the previous hash, as Esteban was mentioning. Every block is chained together with the previous one so that we can make sure that we have that chain pattern, right? And let's add a third property, a fourth property. This is the nonce. And we are going to explain later what's the purpose of this property. For now, let's define it as an integer with 0 value as the default. And we are going to use another property. We're going to create another property called the hash. And for now, we are going to set an empty string for it, right? If you can see, we have one method in here, and let's start coding it. Remember that each block needs to have a hash representation. A hash is nothing more than a string representation passing some input data. In this case, we are gonna pass the properties of a block to the hash function. And for the hash function algorithm, we are gonna use the SHA-256 algorithm. And this is just to generate the hash, right? So let's start creating our hash for this block. And what we're going to do is call the function SHA-256. And we are going to start passing, for example, the timestamp. And we are going to concatenate pretty much every property of a block. We are going to say this dot transaction. But as this is an array, sorry, I just missed here. This is an empty array. And we are going to, as this is an array, we are going to JSON stringify it this way so that it converts into a string and we can just concatenate with other strings, right? And we are gonna say this dot previous hash, and we are going to concatenate this dot nonce. Now that we are using the nonce property, we are going to touch in depth how this is used. But for now, this nonce will give us the opportunity to start generating a different hash every time that we attempt to mine a block. When it comes to mining blocks, remember that we need to start calculating a hash for the block that is going to be added to the chain. So no, don't worry, we are gonna show you how this works in further lessons. But for now, this is the variable that will let us generate a different hash for the given block, right? So okay, that's it for the block file. Let's jump to the blockchain file. And in here, we are gonna pretty much say how our application is going to behave. So let's start defining some properties. I'm gonna create the property called chain. And obviously, as you may know, this is blockchain. We will need a way to store every block that is added to the chain. So for that, we are gonna store those blocks in this property. And obviously, this is an array. For that, for now, I'm just creating this as an empty array. And I'm gonna create another property in here that is difficulty. And for blockchains that use something called, for the consensus protocol, maybe we are going to see this for the lessons. For this example, we are simulating a blockchain that uses proof of work. For example, in the case of Bitcoin that uses proof of work, it means that for every block that needs to be added to the chain, some miners or computers that are in the peer-to-peer network needs to find or to solve a mathematical problem. And the one who solves that mathematical problem is the one that has the rights to add the given block into the chain, right? So this variable in here will help us to set the difficulty for mining a block. You will see later how this works in action. But for now, let's have this in mind. We are going to create a third property called pending transactions. And as every transaction before it can be submitted to the blockchain needs to be evaluated before, right? So what's evaluated in the process? We need to evaluate that, for example, transaction holds valid information, that is a valid recipient and a valid sender, right? And obviously, for example, validating that funds are enough to send, depending the people who is sending the coins. And in real world, this is a very much complex property because it is involved a lot in there. But for now, let's just define this array that will hold every transaction that we want to add to the blockchain. And we are going to add a very, very simple validation, whether the transaction is valid or not, they can be added to the chain, right? And finally, we are gonna create a fourth property called mining reward. Mining reward. And for the consensus protocol, that is when a node mines a block and it can be added to the chain, the computer or the node that wins or solves this mathematical problem receives a reward for their work, right? So for this example, we are going to say that, sorry, this is not an empty array. This is just a number. And we are going to say that the node that is capable to mine a certain block will receive 100 coins as the reward for mining, right? So here you can see the concept of the mining in blockchain, right? You, for example, deploy a node with the software that can mine transactions and you receive coins for your computer to do the work, right? So that's the idea behind mining. And if you see below, we have two more methods, create a Genesis block. As Esteban mentioned, the first block added to the chain is called the Genesis block. So let's implement this function. And what we are going to do here is just create a block class that is from the block file. And we are gonna say new block, and we are gonna pass the timestamp. For JavaScript, we use the date.now function. It returns the Unix timestamp. And we are gonna pass an empty transactions array. As this is the first block in the chain, we don't have any transactions coming through the network, right? So we just set an empty array. And for the previous hash, here we set an empty string because, you know, this is the first block. There are no previous blocks behind it. So that's it. We have our Genesis block created, and let's go back to the constructor. And for this, let's create the empty array, but this time let's use the function that we created. And that's it. Once we initialize this blockchain class, we will have our Genesis block created right at the instance moment. And let's code the last method. For that, in blockchain, it's very useful to know which is the latest block in the chain. That is called the height, as Esteban mentioned. So let's return the last item on our chain variable. And for that, we are going to use the last index on this property, right? And yeah, that's pretty much it. We are going to continue with the theory. This is the way that we are going to work. Once we cover more concepts, we go back to the practical lessons so we can see those in action, right? So I think I leave you guys with Esteban, right?
Yes.
There you go.
Okay, so now we will continue with the transactions of the blockchain, how they work. Next slide, please. So, next one, please. So basically, as we mentioned, the blocks contains transactional information, so they can have multiple transactions inside of them. So a single transaction is basically a small unit of a public record. So this public record could be an exchange of currency, but not necessarily. It could mean like an exchange of information, a signature, or something else. So as I mentioned before, if you try to change information of a block, it will change the hash of the block. But this also applies for the transactions, because each one of the transactions has a hash and also has information related to the persons who sends the transaction and who receives it, and also information like the amount of. And this example is, for example, an exchange of currency. So it says the amount of currency sent, and also the timestamp, which refers to the time the transaction was created. So can we go to the next slide? So digital signing, this is for sending transactions. So we can think of this like when you create an account in a bank. So for that, you need an account. So, to start sending transactions, you need an account. So for this, you need, in blockchain, you need two things, the public key and the private key. These are mathematically generated. This could, in a bank, it would mean your account. And for example, in your plastic, you have a number for your card, and also the 3 numbers in the back, right? So the public key is basically the one that you could share with anyone. This is the information that you could identify yourself publicly. So, for example, transpolated to the bank example, these you can share your, for example, your account number or your 60 numbers of your card, so you can ask for a transaction of money, right? And the private keys should be always kept secret. So, for example, the 3 numbers in the back, or the date of your card, and in this example. So this allows for accountability. The point in blockchain is not to secure or encrypt the message itself. It is to secure the point of origin. So, for example, to ensure that the transactions that are sent by you and no one else. So that's why you shouldn't share your private key, because if someone else has your private key, they could send transactions in your name. So next slide, please. So this is a graphical example. For example, you try to send a message across the network. So you sign a message with your own key. So then you send it to the network, so they can all verify that that message actually comes from you. So next one, please. So we will cover this part in the coding example with David.
Okay, so going back to our files, let's continue with what Esteban was mentioning about the transaction and signing. So for that, let's add a third method into the block file. So this will validate the current transactions for this block. Let's just think for a moment that this method is implemented. I'm gonna write a check in here, and we're gonna use for each transaction on the block. If you see, we are using a for loop to iterate over the transactions property of the block. And for each transaction, we will need to check if that transaction is valid. So this method is not implemented yet, but later we're going to implement it, right? This will return a Boolean value saying that it's valid or not, true or false. If that is not the case, we are just returning false. If everything goes well, we'll just return true, right? And going back to the blockchain file, we are gonna, sorry, not the blockchain file. Let's add a third file here to describe how transactions will behave in this example. So you hit at the same goes for transaction class. We define a constructor having three properties in here. We have a from address, we have to address, and an amount. This is mostly the basic properties that a transaction should comply with. And obviously, from address is the one who tried to send funds to address. This is the recipient or the receiver, and the amount of coins that they want to transfer, right? And the same goes for the transaction. We will need to have a hash representation of this transaction object, because we need to make sure, right, that the transaction, once it's added to the blockchain, we need a way to validate that this transaction hasn't been changed over time, right? So we are pretty much doing the same with the block. We are going to use the SHA-256 algorithm to create a hash representation. And we are going to pass the same properties that we have in the constructor, that is dot from address. We're going to concatenate the to address and also the amount. This dot amount. Okay, cool. And let's just add a third method in here. This is for signing the transaction. As Esteban mentioned, we will need a way to identify ourselves into the blockchain. And that is the purpose of the key pairs. So every key pair holds obviously two keys. One is the public one, and the other one is the private one. So for example, you can see this as an analogy. For example, the public key is your user ID in Facebook, and your private key is your password, right? You share your username or your user ID in Facebook, but not your password, right? This is the same for blockchain. You share with others your public key so they can send you funds or recognize you within the network. And your password is just to authorize to send coins within the network. And you only hold that private key, right? So let's code this sign transaction method. In here, we just receive a key pair. This is just, we're using a library called Elliptic. This is for managing cryptographic functions for key pairs in JavaScript. You can just look for it on NPM, and it's the whole documentation if you have any doubts. So we are using that key pair. And the first thing we are going to do is later when we start coding the mining process, we will need to ensure that we will need to identify whether this transaction is for a reward mining for those blocks that, for example, mine some, for those nodes that mine some blocks. And if that is the case, we will just set the from address to null. You will see further in action, and with return true. This is a valid transaction, right? And let's just make use of the key pair that we're receiving here. We are going to get the X string representation of the key pair. You can get the key representation in any encoding you want. For now, we are going to use the hexadecimal encoding, and we're going to say if the X representation of the key pair that we're receiving in here is different from the address that is sending the transaction, obviously we don't have the permissions to sign transaction for others, right? So for example, you create a transaction, and let's say that your friend wants to send those coins for you. That is not possible because you need a way to authenticate yourself, and your friend doesn't have your private key, right? So that way we make sure that no one can sign transaction for others. And let's just add a couple of properties in here. Let's create a property called hash. And for that, let's say this dot calculate hash. I'm going to use the function that I just created before, this one. And once we have the property hash, we are going to create the signature for this hash. So in a few words, what we sign in here is just the hash representation of this block. That's the way that cryptographic function works. So let's say, let's create a variable called sign, and let's return let's use the key pair. Sorry, key pair, and we are going to use a method called sign. Obviously, this is going to sign the transaction hash for us. And let's copy this in here. We're going to sign the hash of this transaction. And we are going to pass a second parameter that is the encoding that we're going to use for creating the signature, right? There are as well lots of encoding. For this example, we are going to use base 64. And once we have the signature, we are going to use another method to just create the signature property in here. Let's call it .signature. And this signature will hold, this property in here will hold the signature that we just created before, but in another format, right? Sorry, is sign dot to there. This is another encoding that we use to represent the signature. And sorry, this is in may use to there. In here, we're gonna use the X encoding once again. This is pretty much the standard in pretty much all blockchains out there. They represent the signature in X encoding, and obviously you can, for example, verify if the given signature corresponds to any public key. We are going to do that in further lessons. And once we have the signature, let's just print it out. And that's it for our transaction class. And I think we can continue with the theory. Let's do a very quickly recap what we do. We create the transaction class. We obviously add a method to calculate the hash representation for this transaction class. And we add a sign transaction method, which will receive a key pair. Obviously, this key pair will need to match to the from address, so that we just make sure that the person who sends the coins is the same that wants to sign the transaction, or in other words, to authorize this transaction. We create the signature property for the transaction class, and obviously we sign the transaction, we sign the hash with this transaction object. And that's pretty much it. Let's continue with the theory.
Sorry to interrupt you there, David. Before we continue, just to open a very small space for any blocking questions, now that we're passing into the last block of theory. I know we've been covering a lot of topics, and as someone just asked in the channel, well, in the chat, sorry, we've already shared the repo, but we can share the link again. I know we can be going a little bit fast because of time constraints, but the idea is that you just follow along with us right now, and if it's too fast, you can revisit the code. But is everything good so far? Anyone has something in which they are lost that they would like to clarify?
Yeah, I just saw the question that Jill posted on the chat. Yeah, just for keeping things as easily as possible, we just manage one address per wallet. But for example, in more complex examples, we certainly can have multiple key pairs that can manage some funds, or in this case, to have a centralized wallet to manage some funds. But for this example, let's just use a one key pair just to keep things as easy as possible. But yeah, that's possible. That's a good question, indeed.
Awesome. And Jose just shared the repo again in the chat. So if anyone was missing it, you can look at it right there. So
sorry, Bernardo. Just want to add something really quick. Don't think as all the coding we're doing as a specific coin or for a specific technology. This is more of an abstraction. It has a lot a huge amount of weak points. So this should in any way be used as a production environment of any kind. But it is more to illustrate how these basic theoretical parts of a blockchain work together in a more practical way in the code. So it was just a quick note. And anyway, don't try to look for what is from any other blockchain. It's just to illustrate in a more practical way this.
Exactly. And as part of that, as we even mentioned, not all transactions in a blockchain are even asset transfers. We're doing that example because it's like the most day-to-day one, or the most familiar to most people. But yeah, it's just a way for us to illustrate it. And Luis is asking, should we be coding along? No, it's what I'm saying. I mean, if you want to, you're welcome to do it. But if we're going too fast, don't feel like you're falling behind. In the repo, you'll see the final version with all the code. So if you start lagging behind, you won't miss anything. You can have the complete code in there. And well, maybe for time constraints, we can continue answering the questions in the chat, but I think we can continue with the theory. So as you can see, we're missing the block mining, wallets, and that's it. So I'll leave you with Neme.
Okay, thank you, Bernardo. Could you go to the next slide, please? Okay, so I'm gonna be talking about two other concepts that are basics to the blockchain technologies, which are mining and consensus. Okay, so let's talk about mining. As we've seen before, there's a collection of transactions that are expected to be added to the blockchain. In the coding example, this was a variable called pending transactions. So nodes have to take transactions for that pool of transactions and verify them. That's the way blocks are mined. This is different from coins to coins, but the most common example is proof of work. This is used by Bitcoin. So in this process, the miner, the node, has to hash that new block and is hashing over and over again until it complies with an arbitrary constraint. This constraint is just used to make it harder to get a valid block. So once the first miner gets this hash, it can be sent to the blockchain, and this node is rewarded. So miners are indeed getting paid for their work as auditors. And in this process, also new coins are generated. That's the reason we call this mining. We are creating some new coins every time we mine a new block. Next slide, please. So yeah, once a block is mined, a number of nodes have to agree that this block is correct. This is what we call consensus. And we do this because we don't rely on a single entity. Our trust is not put on a single node. And instead of that, we have to rely on a part of the whole network. So it is only until a number of nodes agree that a block is valid that we can include it to the chain. Next slide, please. Yeah. So in this diagram, you can see the whole transaction process. It starts when we create a transaction and sign it. So for example, let's say that Alice wants to send both some coin, 100 coin. Alice has to create a transaction, and she has to sign that transaction using her private key. After that, the transaction gets submitted, and some node mines a new block, including this new transaction. After that, we can send that block. We broadcast this block to some of the other nodes, and these nodes have to verify that block's content. This is the consensus process. Once that those nodes reach consensus, we can be sure that this block is valid. So until that, we produce new coins, which are rewarded to the miners. And after that, this new block is added to the blockchain and distributed to the whole chain. And this is the last step for transaction. And once that's done, we can say that this transaction is confirmed. Could you go to the next slide, please? Yeah, so this last topic is wallets. Next slide, please. Yeah, so a wallet is a secure place to store and access your private keys, which are used for address generation and signing transactions. Maybe a better analogy rather than wallet is a keychain or a checkbook, because the coins are not stored in the wallet. You use the wallet to sign transactions. So similar to a checkbook, you write checks using your signatures, and you use that to send funds. If you lost your wallet, I'm talking about a blockchain wallet, you should be able to recover all your funds if you have the keys associated to it. And yeah, if someone sends your cryptocurrency, it means it is assigned to the address of your blockchain wallet, recorded in a distributed layer, not the wallet itself. Next slide, please. And talking about privacy and security, the blockchain technology has some advantages about this. Some of them are that they do not require personal data to be provided. They just rely on hashes and keys. Another party has to store your sensible information. So in case you don't want to share any of it, you shouldn't have to. Information stored in blockchain is considered immutable. Once it is recorded, it cannot be changed. To change the state of a blockchain, you have to create new blocks, and not that whole history of transformations get stored. So that makes it more secure. And finally, decentralization enhances availability and removes single points of failure. So even if in a given network there are some malicious entities, they won't be able to do something bad by themselves because of the mechanisms that we talked about before, such as consensus. This makes the blockchain technology more secure and reliable. I think we can go back to the coding time.
Yeah, thank you, Nemi. Let me just share my screen once again. Okay, cool. So yeah, now that we have seen how a consensus process is made of, let's just try to reproduce it into our practical example. So let's do a quick recap. So we have the blockchain file, transaction, and we will add a fourth one called wallet. This is for mapping what we just saw in theory regarding wallets. And let's go back to our block file, and we're gonna add a fourth method that is called the mine block. And for this method, remember that the consensus process needs to, in a way, solve a mathematical problem. So for that, what I'm going to do is just use the brute force. This is certainly some blockchains use this protocol. Most of them are the proof of work. And this is just trying to recreating a hash, obviously changing one particularly data on the hash function. Remember that we have the nonce property. So this nonce property will help us to create a different hash each time that we attempt to create one during the consensus process, right? So why we have to create a new hash every time? Remember the property that we have in the blockchain class called difficulty. So for example, in proof of work blockchains, what we will need to do is attempt to create a new hash. Let's start coding. I'm gonna say this.hash. And I'm gonna pick a slice of this string. We are gonna use the substring function in JavaScript. And I'm gonna pick from the 0 index to the difficulty property that we have in the blockchain. So as you can see, we receive the difficulty property in here. So we use that to cut the string out. And what we are going to do with that string is we are gonna compare, and here I'm gonna use a function in JavaScript with the array class, and I'm gonna say the array, I'm gonna create an array with length of difficulty plus 1. And once I have created this array, I'm gonna use the join function. What this is going to do is create an array with this length and then convert this array into a string containing the number of zeros, which I give in this as this property here, right? So for example, if we pass the difficulty as 3, we will receive a number 4 in here. And what we have as an output, we will have a string with 3 zeros. And remember, the difficulty is to set the difficulty of the blockchain, but why we need to set that difficulty? Remember the mathematical problem that we need to solve for adding some blocks in the consensus process. So for example, in blockchain, I think we need to create a hash that has, I think, 11 zeros at the beginning. So as you can see, at the first attempt we do, it's likely impossible to have this result, right? So miners need to have powerful resources to compute these kind of problems. So that is the idea to mining, right? Because computers are trying so hard to find those hashes that meet the difficulty. In this case, having a hash or finding a hash that will meet 3 zeros at the beginning, right? This is very simple difficulty for keep examples easy. But as I mentioned, for Bitcoin, I think there is 11 zeros before each hash. So you can imagine the incredible amount of power that we need to mine those kind of hashes, right? And obviously the node that is able to find this or to solve this problem is the one who claims the reward and can add the next node into the chain, right? So for now, we are going to use the nonce property here, and each time we attempt to create a new hash, we are going to increase the nonce. And if you remember, we initialize the nonce to 0 because every attempt we are going to increase this property, right? And once we increase this property, this will let us to create a different hash. If you remember, we are passing it in here, and if we change any data on here, we are going to get a different output hash from this algorithm function. So once we increase the hash, we are going to say this.hash, and we are going to recalculate the hash using our function from above. So this one over here. So we increase the hash the first iteration, we create another hash if this is not meeting the criteria that we want to find the hash, right? So that's it for mining. Let's just add a couple of console logs just to, at the end that we can run this application, we can see pretty much what's happening behind the scenes, right? We're gonna log the nonce at which we find the hash that meets that criteria and the hash itself. So let's go back to the blockchain file. And for this, I'm gonna add 4 methods in here. We can have pretty much some validations in here that don't matter too much, but let's create a method that will let us add a transaction, right? So we receive the transaction object, and this is obviously as a part of the consensus process, right? To form some blocks with transactions. So before we can add a transaction to the blockchain or to a block, we need to validate the from address and the to address, right? So every transaction, as I mentioned before, needs to have a valid from address and a valid to address. If that is not the case, we cannot add this transaction to the chain. And we are gonna validate, we are gonna use this method that we are gonna create later in here. But for now, we are gonna use this method to ensure that each transaction is valid, right? If that is not valid, obviously we're gonna throw an error. And the last thing we're gonna do is if all these checks are passing in here, we're gonna say that the transaction is valid. And for that, what we are gonna do is use the pending transactions array. This dot pending transaction equal to, sorry, dot push and the transaction that we are receiving in here, right? So we use transaction. And according to this comment, the mempool is the same as pending transactions, right? So mempool is fairly the standard name in blockchain to name these pending transactions. So in these places where miners start picking the transactions as they come in, right? So one way miners can start filtering out transaction is according to one property called the fee. When you send a transaction in the blockchain, you need to specify some sort of a tax for using the blockchain, and that is called the fee. And every transaction that you send through the network needs to have this property, the fee. And validators are taking those transactions that have the higher fees. So the higher fees you specify your transactions, the more likely a validator node pick your transactions to be processed, right? So there are cases, for example, in blockchain that if you specify a very minimum fee, your transaction can lay on this property and this mempool for days until a node can start considering your transactions to be processed, right? So this is a very important thing to remember, the fees for each transaction. And let's add another method. This is mine dependent transaction. As I told you, this transaction needs to pass through a process for validated them. But first of all, let's just create a variable in here that is going to point to the latest block in the chain. Remember that before we can add transactions to a block and afterwards we add that block into the chain, we need to chain together the new block to the latest one. So what we are gonna do in here is I'm gonna just copy some code just to speed up things up. And what I'm gonna do in here is just getting the last block in the chain using the utils that we have defined above. And then we're gonna create a new block, passing the timestamp. We are gonna pass the pending transaction because these transactions are the ones that needs to be included in this new block. And if you see, we make use of the hash of the previous block. Remember that the third property here is the previous hash. So we point to the previous hash in this block. And once this is, once we have the block variable created, we are gonna say block dot mine block. This is the function that we created a couple of minutes ago, this one. And we're gonna pass the difficulty, this dot difficulty. And okay, once we have mined that block, we are gonna push the block in the chain. We are gonna say that this block was mined successfully. And once we have mined this block, we can add it to the chain, right? And there, remember that once a validator mines a block, it receives a reward. So remember that after we mine a block, what we are gonna do is add a new reward transaction to the pending transaction. So once we mine pretty much all transactions that users send to the network, the first transaction of the next block will be a reward for the block, for the validator that actually mined the last block, right? So that's it. We have our mine pending transaction. And these two methods in here are just like very util. So we are gonna, for getting a balance, the balance is the amount of coins that you have in the given address. So what we are gonna do here is iterate over each block in the chain, and then for each transaction on the current block. And we are gonna say that if transaction, sorry, I lose my cursor. Yeah, if transaction dot from address is different from the address that we receive in this method, this is the address to know the balance of. So if from address is equal to the address that we want to know, that is that we send coins out, right? So we're gonna say the balance property that we have above, we're gonna say balance equals minus 1 and the amount, right? Because if the address, the given address is on the from property, this means that that address send coins to another person. If that is the case where this transaction dot to address is equal to the address, it means that we receive coins from this transaction, right? So what we're gonna say here is just add the amount to the balance. And at the end, what we are gonna do is just return the balance, right? And we have added the last method in this class just to validate that pretty much our blockchain object will be validated by these functions. So if you see, we are iterating over each block in the chain, and we are gonna get the current block and the previous block. And this is going to do 3 validations in here. We are gonna check if all transactions in the block are valid, and how we do that is just saying the has valid transactions from the block. Remember that we have coded that method in here. And we are gonna add a 3rd validation in here to check if the current block hash is valid. And for that, we are going to say the current block dot hash is different from, and again, we are gonna recalculate the hash because this function is gonna give us the current hash state of this block, right? If we casually change some data in here, this is going to be different from the actual hash, right? So that way we make sure that, or we realize that someone else changed data into the block, right? So obviously if that happens, the chain is not valid because something bad happened. Something did intentionally this change, and obviously this is considered invalid. If that is the case, return false. If not, we're gonna add a 3rd validation, that is to check the previous hash. Remember that if we change the data of any block, its hash will be recalculated. So the blocks that were chained together back with it will invalidate the previous hash, right? So if you see, we take the previous hash block, we recalculate the hash, and with the current block, we get the previous hash property. And if someone changed data between those blocks, we will know with this validation, right? Because obviously our calculate hash function will throw a different output if some data change. And finally, let's go back to our transaction file, and let's add the last method in here to check if the transaction is valid or not. And for that, we're gonna use a different method from the key pair. Sorry, not the key pair, but we are using another library representing the key pairs. That is the elliptic one. And we're gonna obtain the public key from the address of the transaction, right? In an hexadecimal format. So using this method in here, getting the public key. Once we have the public key, we are gonna verify. And what we are gonna verify here is the hash for this transaction corresponds to the signature that we have in here. Right? And sorry, this needs to be in here, right? So this way we ensure that the given address actually signed the transaction, right? This verify method will take the hash of this transaction and the actual signature of the transaction. And this method, behind the scenes, uses cryptographic functions to derive if the given address was created, the given signature was created using this address, right? And finally, we're gonna create a for file called the wallet address. And once we have seen in theory how a wallet behaves, I'm gonna add two functions. That is create wallet, how to create a key pair using the elliptic function in JavaScript, and how to validate if the given public key belongs to the private key that we are saying, right? So we go back to theory.
Okay, so with that, we've covered all of the topics that we have for today. So I know we're having an interesting conversation in the chat, but now it's time to ask all your questions. So we're having the session right now. Also, can we go to the next slide, please, Jacob? We're going to take advantage of this time while we discuss and we answer all of your questions to put this feedback survey on screen so that you can start answering it. It helps a lot to know your opinion on the course, on the contents of it, how it was presented. But we'll just leave it there so that you have it as a reference, but we can start taking any questions that you may have.
I do have a question, if I may, guys. Thanks a lot for the session. It was great. The first question it comes to my mind is, you mentioned that we have a public and private key, and I cannot stop thinking of, I had a leakage of my private keys. So is there a chance, since I understand that we cannot change anything in the blockchain, is there a chance to replace that with a new private key as soon as I got it stolen, let's say somehow? Because that might represent a security breach, right? I mean, the whole mechanism, if it's not. The other one I have is, I've seen in the news that sometimes there are some providers, please forgive me if I don't say it properly, that they were offering like virtual wallets. You had your wallets, I think, through them, and they all of a sudden disappeared. So is all of the information for those, all of the customers relying on them already lost, already gone, or is there a way to recover that?
Okay, so maybe I can take on the first question. Yeah, so because of the nature of how the addresses work, and this is common for most blockchains I've come across, because it's so intrinsic to how the technology works, is that your private key is basically what gives you complete access to your address, because even as we mentioned, public keys are derived from your private key. So they have like a mathematically relation that cannot be changed, and therefore it's not as, we put that as an example to have a more day-to-day scenario, but it's not as a password that you can just change. Most addresses in a blockchain are directly derived from your private key, and that's why you can share your public key, and that's how the rest of the network will verify, as we saw, right? So if for any reason your private key gets compromised and someone has access to it, they get complete access to your funds. So that's why it's so important, and it's there's such an emphasis on you keeping your private key safe, because it's the only way you can recover those funds. If you lose that private key, you won't be able to recover them either. So this is like a double-edged sword. It gives you, and it's one of the reasons why blockchain enthusiasts think it's a good technology to be used because you're in complete control, but therefore you also have the complete responsibility to keep it safe. If you get your private key exposed, the best thing to do is to just transfer those funds as fast as possible to another account that you have access and no one else has. So I think that answers the first question. Is that where you were?
Yes, thanks.
Okay. And the second question, I think you referred to exchanges, right? All these platforms that help you just manage your accounts and your wallets, and that you've seen some cases in which they get hacked and the funds are lost. Is that where you're?
Yeah, and I think I read in the news like perhaps 3 months back, something like that, that there was a broker and it all of a sudden it was gone and nobody knew what happened there. So I think it's more related to that. Yeah.
Okay, yeah, so when you use one of these platforms, they have a lot of benefits, of course. They help you manage your wallets and they are like a bridge for you to buy new cryptocurrencies or trade between them, because for most users, interacting directly with a blockchain is simply not friendly at all. So these platforms exist for this. They also give you the opportunity to store your keys for you, and that's why you can get some recovery options with them. But you'll also, like, this could be the weakest link in the security of the blockchain, because in the blockchain itself, it can't be hacked. Or just you have like the majority of the power or the presence in the blockchain is how you could maybe influence it. But in big coins such as Bitcoin, Ethereum, all of those is virtually impossible to have the majority of the computing power. But in the case, so it's basically not, it's what we were mentioning. No, it's one of the greatest things of blockchain is that information is immutable. But in the moment that you have an intermediary, such as these brokers, having your keys, then you're trusting the security in them. So in this case, I'm not sure exactly what was the news, but in those cases, what got compromised was the platform itself. Someone got the private keys from them, or even in some cases, even the owners of the platform have made use of this. And as I mentioned, if you have the private key, you can do whatever you want with these funds. So I think it's an important distinction to make. If you hear this kind of news, it's not that the blockchain was compromised in most of the cases, it was one of these platforms.
Cool. Awesome. Thanks for that.
No problem. Any other questions? Something you'd like to discuss?
We might have fell behind in the chat. So if anyone didn't get your question answered in the chat, please go ahead.
If not, then I think, David, you wanted to do a last recap, right? With everything we did in the practical part, maybe we have time just to close everything.
Yeah, that would be very useful. I'm going to show you how what we did, guys, is in action. I'm going to run the application. Let me just share my screen so that you can see how all these concepts are placed into a real world example. Okay. Are you saying my VS Code right?
Yes.
Yes.
Awesome. Cool. So once we have completed the 4 files that we have in here, I was just missing the 4th one. I'm going to explain very quickly what I did. I'm going to create another method called create wallet, and I'm going to use I'm going to make use of this library that I mentioned earlier, the elliptic library, to create every key pair, a public and a private one. And I'm going to create another function to derive the public key from the private one. This is very useful in some blockchains to verify the authenticity of both key pairs of a key pair. And I'm going to return true if the given private key matches the public key, right? And once we have that in place, we can just run our example. I have prepared a very to debug our application, and I'm gonna create an instance of our blockchain class. So this will mine the transactions, create the transaction for us, and all that stuff. I'm gonna use the create wallet method that we saw just earlier to create wallets for my wallet and for Ali's wallet, following the example that we saw on the slides. And what I'm gonna do is just outputting those key pairs. And I'm gonna create the first transaction, passing the public key from my wallet. I'm gonna transfer some funds to Ali's wallet using her private key. And I'm gonna transfer this amount of coins, 60 coins. Then I'm gonna sign the transactions with my wallet key pair, since I'm the one who signed this transaction. Once I sign that transaction, I'm gonna add the transaction to the blockchain. And I'm gonna, after I add this transaction to the blockchain, I'm gonna mine that transaction using our simple blockchain object, obviously passing my wallet public key, right? And I'm gonna do the same for other two transactions. So in total, we will have 3 transactions created. Each transaction will be included into a block when we call the mine pending transaction. Remember that the consensus process is in action, and every transaction that is in the pending transactions array will be included in the next block, right? And I'm gonna do a couple of things below here. What I'm gonna do is just, after I did the transactions, I'm gonna check for the balance, Ali's balance, and I'm gonna use the get balance address, right? So this will output how many coins they have for the given public key. And then I'm gonna call the isValid chain. This would, remember that this is just to validate if everything in the network is okay, if none of the blocks has been altered or modified, or even transactions. This will output true, and afterwards I'm gonna change one data of one of the transactions. I'm gonna modify it and say that I just transferred 200 funds, 200 coins. And obviously, as I change some data, this function will output false, because remember that we recalculate the hash for each transaction and for each node, and the hashes will be different, right? After I change this property. And at the end, I'm gonna just pre-print in JSON format what our simple blockchain object looks like, right? So let's do the debug. I'm gonna run. And as you can see, let me just make, okay, right here. So if you can see, we are just outputting some stuff in here. We create the wallet, my wallet public key and private key, and the same for the Ali's wallet, right? So if you see, there are lots of, well, not lots of blocks. There are 3 blocks mined. We have the nodes at which we found the hash, and we have the corresponding hashes of each block, right? And if you see, we are mining each block. The three blocks are being mined. And once we have mined pretty much all the blocks, we output the balance of Ali's. And if you can see, if you adding every amount in the transaction, you will have this number in here as the total balance for Ali's. The first call to the isValid chain is outputting true, and the second one is false, because we already changed some data, right? And at the end, we have pretty much the whole object. If you can see, this is the Genesis block. It doesn't have any transaction. And for each block, if you see, we will have, remember that difficulty property that we saw? If you see, every block has 3 zeros at the beginning. This is the first block. It has 3 zeros. The next one has 3 zeros, and it's completely different. And obviously, we have the reference to each one. We have to the first block, to the second block. It is referencing to this block of here, the Genesis block, and so on for each one. We have the transactions, and we have obviously at the end, we have some, in the pending transactions arrive, remember that we add a reward for each validator that solved the problem. And we have this transaction reward for the last miner. And that's pretty much it. As you see, we are just implemented a very basic blockchain using JavaScript. We will give you the link so you can play around with it. And I leave you with Bernardo.
Thank you, David. We wanted to take the opportunity to wrap up everything. Hopefully that last example helped things come together, all the concepts. We're running out of time, but if anyone has the last question, we're leaving the feedback survey here. Jacob has been sharing it as well in the chat. Someone asked if we're planning to have further courses related to this, and yes, stay tuned for that. This was meant to be an introduction only. We're planning to make some courses with more specific topics. Someone mentioned smart contracts, that could be part of it. And we'll just dive in a little deeper now that you have the foundations. So definitely stay tuned. I don't know if anyone has any extra comments from the team, something you want to add?
Nope, just
Nope.
Thank you guys for assistance to this course. So hopefully you enjoy this.
Awesome. Thank you very much. Yeah, all resources will be shared, the repo, the slides, and the recording. So thanks a lot for joining. Jacob, anything to add? So, no.
Nothing else. Thank you, everyone. Thank you, team. It was great. And I hope you all have a great afternoon. See you all.
Have a great day. Bye.
Bye.